Hello and welcome to.
Hello, and
Whoa, come on now. Hello and welcome to Roid Rage. I'm Jack Beyer. I'm head of media here at AstroForge, and today we are doing something a little bit different and a little bit special. Joining me is Andy Ryan.
yes.
What's your title? Just give us. Oh no, fuck that. Let's start over. See, that's the worst part about starting over multiple times is now it's like now it's like if it's not perfect, we're gonna start over. All right.
No more do-overs.
This is it.
Center your chi.
Joke's on you. I don't have chi. Hello and welcome to Roid Rage, episode 56. I'm Jack Beyer, head of media here at AstroForge, and I'm joined by Andy Ryan. What is your title, Andy?
I am AstroForge's Senior Payload Scientist.
Awesome. Well, this is going to be a little bit different today and a little bit special because you just had sort of a major announcement, did you not?
Yeah, we just released a scientific paper on the analysis of samples from Bennu that we've been working on for the last 2 years. This was a study I completed right before joining AstroForge, and really excited that it's finally out in the wild now.
Yeah, this is going to be super interesting as we delve into some of the science that has been freshly released about OSIRIS-REx's mission to the asteroid Bennu. Now, in case you've been living under a boulder, that's terrible.
That'll make sense later.
Yeah, in case you've been living under a boulder, in a nutshell, NASA constructed the OSIRIS-REx mission to sample what they expected to be a sandy asteroid, and when the spacecraft got there, they sort of found a rock quarry instead. So when OSIRIS-REx arrived at Bennu in 2018, it was, basically all boulders. Is that a fair characterization?
Yeah, boulders all the way down.
Nice.
Yeah, which presented a real challenge for collecting those samples. So the whole mission architecture and the sampling mechanism in particular were designed with the expectation that there would at least be some areas on the asteroid that had finer particulate materials. So, things that are like pebble size down to sand size or even finer than that. And those expectations were set based on a combination of remote sensing data, which is basically telescopic data, and what we had seen at the very few asteroids that had been previously visited by other robotic spacecraft. So we were going on, admittedly, really limited data. And part of the reason we do these missions is to learn something new. And we learned something new right away as soon as we got there. We had expected that the asteroid would have boulders on it. It was suspected that asteroid Bennu is what we call a rubble pile, which basically is just an asteroid composed of fragments from the collisional breakup. So basically you have a larger, what we call parent body, a larger parent asteroid smashed into maybe another one. They completely got obliterated, and some of those fragments came back together gravitationally, and you get Bennu. So it was strongly suspected Bennu is a rubble pile. And one rubble pile had been visited previously by the Japanese mission, Hayabusa. And that rubble pile, Itokawa, had lots of boulders, but it also had seas, so to speak, of finer, they look smoother because they're just composed of smaller, finer particles. And so that was kind of the expectation. Okay, we're going to find a rubble pile. We're going to find lots of boulders, but we're also likely to find some of these finer seas like they saw in Itokawa. And the telescopic data that we had, our remote sensing data, seemed to be consistent with that. So that's how things were designed.
I shudder to think of what it was like for the people that designed the tag SAM, the sampling mechanism, and we get the imagery back and they're like, oh no, like we did not build this for this.
Yeah, it wasn't like a singular moment where we got an image and we're like, oh, it's boulders everywhere. As you're approaching the asteroid, and I remember this really well because it was, it gets bigger and bigger over a period of a few weeks to months. It starts out as a single pixel, and we're all celebrating like, all right, we can see the asteroid. It's 1 pixel, like we're on our way.
Yeah.
And that's really cool because that's where it starts to really become real. All right, we're here. And it gradually gets bigger and bigger and bigger. And as it got bigger, you start to see things. You say, okay, I can see like there's this really big boulder that's, 30, 40, 50 meters tall sticking up in the southern hemisphere. And that's actually one we saw in the radar data. So we knew that one was going to be there. And we're like, there's that big boulder sticking out. Cool. The radar model was correct. And then it gets bigger and you're like, okay, we can see some other really big boulders on the surface. Cool. Like it looks like a rubble pile, and it gets bigger. And you just keep seeing more and more boulders. And at first it looked like there were areas that were smooth. And we thought, well, we see smooth patches. That's probably the good sampleable stuff that we're going to want to go after. But as we collected more data and got higher and higher resolution looks at the asteroid, those smooth areas turned out to be covered in boulders too. They were just smaller boulders. They were, on the order of like a meter or more in size. So like the size of this chair I'm sitting in, this is not an easy thing to pick up by a spacecraft. So although it looked smoother, you zoom in and it's just meter or even, tens of centimeter sized boulders kind of throughout the asteroid. And I think so it was kind of like a slow dawning on the team, like, oh crap, this is going to be harder than we thought.
Oops, all boulders.
Yeah. Exactly.
Yeah. Holy cow. So here at AstroForge, we are not targeting rubble piles with Deep Space 2 and follow-on spacecraft. We are targeting M-class asteroids that are supposed to be, theorized to be, just like a monolithic hunk of metal. Is that a fair, like, you're the scientist, I'm just a guy that points cameras and takes pictures and videos and whatnot. Like, is an M-type asteroid like a single chunk of metal in theory, or is it also kind of bouldery, just a different composition? Like, what's the delta there?
So that is a really good question. And I wish I knew, conclusively what every M-type asteroid is going to look like, but we don't have a crystal ball yet. We haven't really visited M-type asteroids before. So I think we're going to learn a lot as we start to explore these bodies. The Psyche mission is on its way to an asteroid that is also called Psyche. That's a much larger M-type asteroid than the kind that we intend to visit. So although we'll learn a lot from it, everything that's learned there may not be directly mappable to the types of objects that we plan to visit. But the goal is to find, like 100-meter class in terms of total size, monolithic metallic asteroids. And I do think that they should exist out there. Just when you have a small enough body, it has essentially no gravity. Like the gravity is in the micro G range. And so any material that's on the surface is barely bound to the surface. And some of these objects spin relatively quickly. So you cover a big chunk of metal and maybe it does have particles on the surface that could be generated from meteorite impacts over time. But as they spin and spin and spin, those materials are just spun off the surface. So I think it is reasonable that there should be metallic monolithic asteroids out there. And that is what we intend to find.
It's going to be so exciting when we have a spacecraft headed towards an asteroid, and it's the same kind of deal, like you just said, where it's like 1 pixel off in the distance, and then slowly we get a couple more pixels, and then slowly we get to resolve like some light and shadow. I'm really excited.
Yeah, that's going to be such an amazing moment, and it's a moment that hopefully we will do numerous times, because I think like the OSIRIS-REx mission and the lessons learned from that really illustrate how important it is to just go to an asteroid, because you're always going to learn something. And so right now we've had spacecraft visit, like, I could count them on one hand how many asteroids like we've really visited up close and interrogated, and each one is different in its own way. And so the more shots on goal you get, the more data points you're able to collect, the more we'll really be able to like hone in on the solution and optimize our mining technology.
It sort of feels like it's always a little bit tragic to me that so many of these missions that deliver such amazing science that so many people work so hard on are like multi-decadal affairs. And it's like, if it messes up, well, that was our one. You know what I mean? One of the things that really makes me stoked about being here at AstroForge is like, we should be sending a lot. Like, we should be able to do a whole bunch of science rapidly and not just wait, this is one person's entire scientific career waiting for this one probe. Like, that is just not the way I would want things to be done if I could just wave my magic wand. And, there's like the whole, we know more about the surface of the moon than we do the bottom of the oceans and what have you. Like, well, we know more about the bottom of the oceans than we do asteroids, seemingly. Yeah. And maybe we should know more about everything.
Yeah, I agree. I think that we really do need to just start visiting a lot more of these objects and doing it faster and at a lower cost. And, of course, that's like the dream, to make missions cheaper. And NASA has been trying to do this for decades. But I think we're finally at the point where we could start to make that happen by sending these low-cost missions. And we don't need exquisite, extremely expensive payload suites on every one of these missions, which is part of the reason that, it turns into this multi-year, decade timescale thing, because, you have to make sure that it's like a 99.9% of success. You're going to get all the measurements that you ever want to get all in one shot, just because you don't know if you'll get to do this again. Instead, we can go more cheaply, faster, and you can learn a lot with just a camera. So just getting like a survey of what's out there is gonna like blow the doors off of things, I think.
So exciting. I mean, we'll get to learn not only about different types of asteroids and how they're composed and whatnot, but that I'm sure will also give us clues in terms of how solar systems are formed, how planetary bodies accrete, or whatever the appropriate word is. I'm not a scientist.
We'll learn a lot about the scientific history of our solar system, and just the process of planet formation and the dynamics of asteroid families and things like that. We'll learn a lot that will inform our mining objectives, but we'll also learn a lot that can inform planetary defense. We're going to be visiting a lot of near-Earth objects. Many of these objects, could someday be on a crash course with Earth. Near-Earth objects they orbit the sun, and they have an orbit around the sun that is, similar to the distance that Earth orbits the sun. And so every so often, those orbital paths will cross. And so that was the purpose of like the DART mission. They intentionally crashed into an object just to understand how much they could perturb it. And so that was, again, one data point. It was extremely valuable, but the more of these that we're able to see, the more we can start to create better mitigation strategies.
Which I think we can all agree would be a good thing. I mean, planetary defense. I like our planet. We should defend. We should be able to defend it properly.
Yeah.
Cool. So you've been on the podcast before to talk payloads specifically, but with the release of this paper, I just wanted to get you back on, and we're going to talk about the paper and everything in it here in just a second. But first things first, I guess now we're like second or third thing. But either way, let's just, for those who are watching or listening out there who don't know you, don't know your bona fides, give us just like a quick elevator pitch. How'd you get started in this field, and how did you get started on the OSIRIS-REx team?
Yeah, so I went to grad school in planetary science, and I was fortunate to work with a PhD advisor that was involved in the OSIRIS-REx mission. So OSIRIS-REx was selected for flight by NASA in 2011, and I started my PhD program like 2 months later.
Wow.
And my PhD advisor at Arizona State was part of that selection, and he was providing one of the scientific payloads that went on the mission. So people often ask me, how do you get involved in planetary science missions? And there are kind of, there are like 2 or 3 ways to do it. If you're a young student, one of the best ways to do it is to work with a PhD advisor that's on one of the missions, which is what I did. There are participating scientist programs, or, once you're far enough along in your career, you start proposing those missions. So I took the easier path and just, kind of tagged along with someone that was already involved. And so as they were building the OSIRIS-REx thermal emission spectrometer at Arizona State, we were starting to think about what type of science we would do with that instrument. This is an instrument that measures the temperature of the surface of the asteroid.
It's like a really fancy laser thermometer that you would get from like Home Depot.
Sort of, yeah, essentially. And so,
yeah. Sorry, I don't mean to just immediately.
No, it's a good analogy. It is exactly that kind of technology where it's a non-contact, like kind of laser. Like there's no laser involved, but you're measuring the heat coming off the surface, and you can get temperature from that. And so as the spacecraft orbits the asteroid, you build up these temperature maps. And the reason we care about temperature is because as temperature fluctuates during the day, heats up, and at night cools down, basically the range of those swings in temperature, or the amplitude of those temperature swings, that's attributed to something we call thermal inertia. It's, I don't want to get too deep into the science weeds right now, but
I do.
Okay,
actually,
well,
I have a question in a little bit, but
yeah.
we'll get there. But
basically, it tells you about the material nature of the surface, like the physical properties. And so the intent was that, because we were expecting there to be these fine regions of particles that would be sampleable, And we knew that the sample mechanism was being designed to accept particles of a certain size. It basically, the opening on the sampler was basically, about 2 centimeters wide. So we had this driver to be able to identify where are the particles that are smaller than about 2 centimeters. Now, we don't want to fly down to the surface every time we want to like poke around. And our cameras were, the cameras are very nice, but they were definitely not nice enough to be able to resolve sub-centimeter stuff from, many kilometers away.
Right.
And so this is a way to do that indirectly, where it turns out that those thermal fluctuations actually can be related to the size of particles when you have just like, a sea of small particles. So in grad school, as the instrument was being built, I devised laboratory experiments to start to build up ways to measure heat flow through simulated asteroid soil with different particle sizes so that we could predict, know how to do that prediction when we got there. So that was how I started. So I started attending this OSIRIS-REx team meetings. I got to go to the launch in 2016, which was really exciting.
Heck yeah.
And shortly after that, I defended my PhD and continued on in participating in the mission. Did a postdoc in France with some co-Is on the mission to kind of create a numerical, like a computer simulation model that accompanies the lab results that I had. So everything was moving towards, we're going to apply everything that we've learned from the lab measurements and this new fancy numerical model to finding where to collect samples on the asteroid. So I was like, all right, I'm ready to go. I got the tools. We've done our homework. Let's get to the asteroid. I finished my year in France and continued my postdoc at University of Arizona in Tucson, which is the hub of the OSIRIS-REx mission. And I arrived in Tucson basically right when we arrived at the asteroid.
Nice.
And that's when all shit hit the fan. Because it was basically like, oh, turns out I can't apply anything that I've learned and developed from my lab experiments in this fancy model because it doesn't look like there are any regions of fine particles. So it's kind of like, all right, we got to pivot. Anyway, I think I was answering your question of how I got involved. Well, that was the story of how I got involved.
That's fantastic. What was it like to be on the mission from so early on and now well, first off, let's stick with that one. And it's a two-parter, but what was it like to be on the mission from like such an early stage?
It was really exciting. Early on, I think that I didn't realize what I'd signed myself up for or how long I would get to remain involved. I think I was just happy to be involved in whatever way was possible. So initially I thought like, cool, I'm going to get to do these lab measurements and then I'll, probably be sent off and I'll go do something else.
I frequently am like super thankful to past Jack for things that he decided to do.
Yeah.
Are you like super thankful for past Andy?
Yeah, this is like one of those like internet memes now where it's like, tell your past, or what's that like format right now? It's like
someday someone will ask you to
10 years ago, someone will ask you to do this laboratory experiment. It's very important that you agree to do it. It was exactly that because I remember when we had the idea to do that experiment and to do the model, I was like, I don't know if I really want to get into modeling, and I'm glad I did, and I ended up liking it too. So
heck yeah.
What was the question? Oh yeah, what was it like early on? Yeah, so it was kind of like that initially, and attending the science team meetings, I was, this like second year PhD student. I was very nervous because it was like a lot of really well-established scientists. So I was kind of scared to really speak up. Or, if there were like discussions, I wouldn't really speak up because I felt like, oh, I don't know enough here. Like no one's going to want to hear what I have to say. And it took me a while to get over that, and I think that's true for most people. Like you initially, you have that imposter syndrome, and to a certain degree, you're the new person. So you're not an imposter, but like, kind of just got to sit and absorb for a little while. And so that's what I was doing. And it was fascinating. There were some like, I'm not going to go into anecdotes on early mission, but yeah, it was fun. And I kind of like gradually developed my confidence. And then by the time that we arrived at the asteroid and I was a postdoc, I'd finished my PhD. I was part of what was called the thermal analysis working group at the time. I had like the confidence where it's like, I know my area of expertise well enough that like I'm willing to, speak up and participate in these science discussions now. And to a certain degree, you kind of just got to like push yourself to do it.
I
Otherwise, you'll just sit there and never say anything.
Yeah, no, I am like, just to be like a little bit inside baseball, dude. I struggle with imposter syndrome and have my entire life. Even when I'm like hitting home runs left and right, or at least feel like I am internally, there's always that voice in my head that's like, yeah, but what if you're awful? It's like, thanks,
think-
brain. Like
I think
brains are.
that's true for just about everyone. Like, there are the true extroverts out there that maybe don't struggle with that as much, but like I'm not one of those people. So it
Yeah.
always takes a lot of energy to like really get myself out there. And so part of participating in that mission was an exercise, forcing myself to get myself out there and to be outspoken. And that ultimately really helped me out a lot because that's what led me to the opportunity that led to the paper that we're going to be eventually talking about
Well,
here.
we'll get there, I promise. So you started out very, not senior, but you ended up as the what was it? Sorry, lead scientist on that working group, or how
Yeah,
does?
I was called the working group lead, and it was kind of means lead scientist, but also lead cat herder,
Right.
lead orchestrator. So yeah, fast forwarding a little bit when it came time for the samples to come back, and we successfully did ultimately collect samples. We found that there were some few very rare regions that did have smaller particles. They looked like they were mostly fresh impact craters, where their impactors had either unearthed smaller particles below the surface or smashed them up. There are different hypotheses. We got those samples. They were on their way back, and it was time to create the analysis plan. And so the analysis plan was it was divided by scientific discipline, as I mentioned, or maybe I didn't mention, I don't remember, where you had these different groups. There was one for elements and isotopes, one for organics, which there's been a lot of press coverage because their papers came out about a year ago now, I think, where they found a bunch of amino acids and proteins and really fascinating stuff. There was one for mineralogy and petrology, so that's like kind of understanding the geologic nature of the materials. Let's see, elements and isotopes, organics, mineralogy, petrology. There was a spectroscopy group, which I won't go into because, well, Matt's not here. I could, but that's basically a specific technique for analyzing the samples. And then Dante
Wait.
Loretta came to me. He's the head of the mission and said, we have in our plan, we've had in the plan from the beginning that we would measure the thermal properties of the return sample and all those other things I just mentioned. All those other things, we know who's leading those efforts. Some of them have been signed on from the beginning, from when we wrote the proposal for the mission, but we really never had a really laid out plan for the thermal measurements. So he said, can you figure that out for us? Oh, and because we've realized that these boulders on the surface may be weird based on the thermal results we got, we should probably measure thermal and physical properties kind of in concert together. And so that was the start of that. And you could, I could be here all day speculating on why that opportunity came to me. Part of it was just working really hard and being outspoken and trying to understand what the hell we were looking at on that asteroid and talking to senior management as much as you can and just brainstorming and trying to come up with experimental technique ideas for how we could measure the samples when they came back, but that's basically it. So I was given a budget and basically a blank slate saying, go ahead and create the plan.
That's so cool.
So that was in, we collected the samples and we departed the asteroid in 2020, I think.
Also, side note, if anybody out there has somehow like existed for 6 years after this and not seen the footage of the Tag Sam booping Bennu, it is some of the most wild footage that's ever been shot.
The surface basically exploded because
like when you guys saw that? What was your reaction? Were you like, oh no, like? And then I also like I have so many questions. I will try and give them to you one at a time.
Yeah, no, I'm happy to. I mean, I obviously like discussing this, so I'm happy to answer all these. Hopefully, the audience will feel the same way. Yeah, so the surface basically exploded when we touched it. That goes back to this is a really small asteroid. It's only about 500 meters in diameter.
It's a rubble pile.
It's a rubble pile, and the gravity is super, super weak. And so we touched it, and basically just plowed right through it, and particles just started shooting everywhere. We did eject gas, which was part of the sample collection mechanism, was to intentionally stir things up, and that was like a bomb going off when we ejected that gas. So how did the team feel? I mean, by the time we got the images, the event was over.
Right.
So there was no like, oh no, what do we do? Do we back away? You know, like the execution was done. It was more like, whoa, that happened, and you know, let's check and make sure the spacecraft is healthy and all that good stuff. And it turned out like we're okay. We were able to back away, and you know, there was a lot of activity kind of at the management level to assess like the success of the sample collection. So they were taking photos and making sure like we got stuff, and it looked like, yeah, we did. Let's stow it, make sure we've got it, and it's safe. Because one of the key decision points that had to be made was, do we try again if that one didn't work? And we quickly decided, no, we're not trying again. It's too risky, especially after what we just saw.
Right.
Let's you know, stop while we're ahead and
Did
take
it-
this back. But the moment was really exciting. It happened. It was in the middle of the night. Well, actually, it's funny. The OSIRIS-REx sampling event was, I remember now, it was October 20th, 2020, because that was 3 days after I got married.
Holy cow.
And
Oh,
I was in
man.
France at the time, and it was happening. The data were coming down, and it was around 11 p.m. in Europe. So it was like 4 a.m. or no, it was like middle afternoon, or I don't remember. And I was laying in bed, and my wife fallen asleep, and I was just on like the team chat that we had through Slack or whatever it was, and
Yeah.
you know, everyone just freaking out, and you know, initial images coming down, and you know, just it was fun, just because the team is just like, the team was all spread out. This was during the pandemic, so pretty much everyone was remote, and you know, just there was the initial kind of live play-by-play where they knew it was happening, and then there was like a 6 or 7 hour pause, and it was actually the next morning, just as I was waking up, that the first images were coming down, and that's where it was really fun in the team chat, just being like, holy crap, like, look at the surface, you know, how much it exploded, and people immediately analyzing the images, you know, passing around, like annotating the images, marking things, pointing things out, sending it back through the team chat, be like, look at how this rock here moved, and look at like what we did over there. And so that's the fun part of being on these big science teams, is because you've got like so many experts from so many different backgrounds that, like, you know, this person will point out this one thing, and you're like, holy crap, I would have never thought to notice that, but like, I'm so glad that you're here, because that is really cool what you just pointed out. So yeah, that was a really special time. And even before that, like before the pandemic, when we were all in Tucson together, and we were in like an open cubicle space, and there were about like 30 or 40 scientists all in this area, international. So we had a bunch of people from the US, but we had a lot of people from all over Europe. We had people from Japan. Super cool, just like amazing atmosphere to be working in.
So awesome. All right, let's talk a bit more about the paper in detail now. Way back in 2007, the Spitzer Space Telescope showed that the surface of Bennu heats and cools rapidly like a sandy beach. So that's what NASA expected to see when the spacecraft got there. Earlier in the pod, you said the words thermal inertia. Please explain thermal inertia like I'm 5.
So thermal inertia is, I talked about it a little bit before. It just is how easily something heats up during the day and how rapidly it cools off at night. So certain materials heat up really quickly and cool down and get really cold at night, and others are kind of more muted. It's like the difference between sand, where it gets really hot in the sun on the beach and you can burn your feet really easily, versus a nice bouldery surface, or even like a brick wall, and vice versa. At night, the sand gets very cold, whereas, you know, you stand next to a brick wall in a building, you can still feel the heat radiating off of it. And that difference is just due to how heat can flow through those materials. So sand, it's made up of all these little particles.
It's like a crap load of surface area.
Yeah, there's just lots of little contacts, and it's very hard for the heat to make its way through. Whereas, you know, a brick or a boulder surface, you've got just this nice, dense medium, and heat is able to effectively conduct through it. And so we can look at those temperature fluctuations to learn about what's on the surface of an object, including an asteroid, without actually having to go to the surface or having a crazy, crazy, super high resolution camera that can see, you know, millimeter-sized particles or whatever. So yeah, the Spitzer Space Telescope, we were able to fit it with thermal models and extract a thermal inertia estimate, and the value kind of sat between rock has a really high thermal inertia and dust has a really low thermal inertia, and it was sort of in between. So we thought, all right, that's pretty good evidence that we're probably seeing some rock and some small stuff. We're seeing a mixture of those two signatures.
Right.
That's consistent with what Hayabusa saw at Itokawa. You can make some basic assumptions and say, what if the whole asteroid is covered in the same particle size, and you can calculate a particle size from the thermal inertia, and the particle size was like a couple centimeters. So we're like, all right, that's pretty good evidence that there should be stuff smaller than that on the surface. And the radar data seem to indicate that too. The radar data show that the upper surface, the way that the radar scattered on the surface was indicative of it being not very dense.
Okay, so we have these observations. We, based on the thermal inertia measurements, expect it to be a certain way, and it was completely not that way. So we have a heat problem. And the rocks were sort of expected to be porous once you realized it was boulders. Is that correct? They're the only explanation for this discrepancy is that the rocks are really frickin' porous. But it turns out the porousness did not account for all of the discrepancy there. Is that a fair characterization?
Yeah, so we had known beforehand that rocks can have different properties and of course different thermal inertia values. It was just this was far more extreme than really anyone had anticipated or planned for. If you apply some really simple models, it would, some of them were predicting that the rocks are 50% void space, which is just way higher than any meteorite that had ever been measured. We also saw that there were distinct populations of rocks on the surface of the asteroid because we saw trends in thermal inertia. Some areas were high and some were low because we were able to map those temperatures. The areas with the lowest thermal inertia, which would be indicative of the most pore space or the weakest, most void-filled rocks, that corresponded with areas that had more of the really dark, really jagged, rubbly-looking boulders. The areas with higher thermal inertia had boulders that were more angular and block-like with sharp corners, and they're more square or geometric in shape, and they're slightly brighter and had smoother surfaces. So that kind of clued us in, okay, the thermal trends we're seeing here don't really have anything to do with the relative abundance of boulders versus fine sand and dust and whatever. It's just boulder A and boulder B. We're seeing two types, and they just are distributed in different ways across the surface. And so that's kind of that was the end of the chapter of the spacecraft at the asteroid. We took the information that we had and we wrote papers about it and said, all right, here's what we think. We think that there are two different boulder types that dominate the surface. They appear to have different thermal properties, which means they probably have different physical properties. The dark ones appear to be really porous, which may have implications for, if you crash into one, how it would respond.
How porous are we talking? Is it space pumice?
No, not quite. 50%, whereas pumice is 80 or,
okay.
Yeah, not quite that high, but for comparison, the analogous meteorites that we had analyzed had porosities no higher than 20 or 30%. So this was double. So we're whoa, okay, these are exotic materials. And we did speculate, maybe we don't have any of these on Earth because, we have meteorites that enter Earth's atmosphere and they're fireballs. And maybe if this stuff ever came through the atmosphere, it would just be obliterated. So maybe we could never get something like this via natural sample delivery, which is AKA just a meteorite fall.
Yeah.
Yeah. So that's where we left off. We're all right, that chapter's closed. We've collected samples and we're going to bring them back and try to figure out if we were right. So part of this exercise is just testing the hypotheses we made when we were at the asteroid.
That's science at its finest.
Yeah,
you see you make an observation. Maybe you're surprised at the time you're making the observation. It's not what you expect, and then you make some hypotheses and you test the hypotheses.
Yeah. And so one of them was that these dark boulders are super porous, but it also was speculated maybe they're cracked in a particular way that inhibits heat flow too. So I'm not going to say that because one of the findings in my paper where we analyzed the actual samples was that they are extremely cracked, and that's one of the reasons they had a low thermal inertia. That wasn't necessarily a surprise to us. It was just really hard to prove through the measurements, which is one of the reasons that the paper I feel was a big advancement. So that it wasn't just a straightforward thing to do. And so that was one of the things we wanted to do is understand What are the relative roles? And, just like even higher level, like when we look at another asteroid and we get a thermal inertia estimate moving forward, how do we even interpret that? Because we've been fooled once before.
Right.
So what's the path forward now? And to do that, you kind of got to, bringing the samples back and being able to look at the actual microstructure and be like, that's why is an important part of that process.
When the TagSam, when the little collector thingy was having issues with the closure of the container, what is the vibe like in the group chat at a time like that? Like I can't imagine
Yeah.
that was super fun or like chill.
That's a good question to ask Dante if you ever get him on the show, because he was the one who had to deal with that situation. I was not a part of those conversations, but I think that there was an extreme sense of urgency to decide, because they knew that every moment they waited, particles were leaking out and that mass was going down. So they had to decide, do we stow and go home, or do we try again? And so originally we were going to wait like weeks before making any decision. And they were even going to like spin the spacecraft around with the arm extended to try to get a mass measurement.
Yep.
Basically like a moment of inertia thing. And they
Like we knew how we would spin previously. Now we know how we're spinning with this sample. Therefore, there's that much weight in it, kind of thing.
Exactly. Yeah. And they said, no, we're not doing that. Like,
just stow it.
Stow it.
Just stow and go.
So some of that is, like the PI Dante having to work with NASA, and there's a formal decision-making process that needs to be carried out in order to make those really critical mission decisions like that, like the decision to stow the sample. Certain people are required to sign off on that, so I think that they were just expediting that.
Makes sense. So did you at any point expect this like extreme cracking of the rocks to be the answer for the heat discrepancy, or was that like a total surprise? I guess you kind of said that you thought there might be some cracking.
I honestly thought that was going to be the explanation.
Nice.
Yeah. Yeah, it was definitely predicted, and there were even like some papers where people had published just like theoretical models showing like if like this is your boulder surface and you have one crack below the surface that's parallel to the surface, you can suppress the thermal inertia enough to create the signature that we saw. I was always a little skeptical, though, this idea that there would just be one perfect infinite crack at just the right depth below the surface. But I figured like cracks are going to be a part of it. One of my concerns, though, was that if that's not the explanation, and it is indeed that these things are just super porous and almost like fluffy, that the process of collecting and returning the sample would obliterate those materials, because they'd get shaken up so much, we'd open it up, and that material would no longer exist.
It'd just be like dust, basically.
Yeah.
Wow.
Yeah. So part of our initial triage of the sample was trying to compare the big particles to the small ones to see if there was like this discrepancy, like maybe the big ones were only the hardest ones, and all the small stuff, like maybe you'd find the fluffy stuff like relegated to the finer particle sizes because it all got broken up.
Right.
But we didn't really see compelling evidence for that. But, we were definitely on the lookout for that as a possible explanation.
God, that would be... Oh man, just like to go through all the trouble to actually collect a sample, to actually get the thing closed and stowed, and then you get it back and it's all just like obliterated dust. It'd be like going to the grocery store and you get home and it's just like all your eggs are smashed or something, but like times $800 million or something.
But this whole porosity and density thing actually fed into the initial triage of the sample in a really important way, because we had predicted that there may be really big differences between particles in their density, or really their porosity. So, high porosity, low density. We built in ways to measure density and porosity in the curatorial facilities at NASA Johnson Space Center without contaminating the samples. Because the science team, we had a certain budget, a mass budget. This is the amount of sample we're allowed to take out of the clean rooms and analyze, and it becomes effectively contaminated at that point. The mission as a whole, and NASA decided that they were going to save about 70% of the sample for long-term curation, future analysis. A great example of that is the Apollo samples.
Right. Except for all the ones that guy stole. Sorry, go ahead.
But a bunch of like new Apollo core tubes that had never been opened were recently analyzed because, we had the patience to wait 60 years for technology and analysis techniques to improve. They were able to do amazing things that would have never been possible back in the 60s and 70s. And so, same thing, a lot of the OSIRIS-REx samples are stored for future generations. So, we had a budget. One of the ways that I decided we could get around that budget was if we could do measurements in the curation facility, in the clean rooms, in the boxes that are purged with ultra pure nitrogen where the samples are actually stored. So basically a non-invasive measurement technique that allows you to learn something about the sample without actually counting it against our, without having to put it on our tab.
Right.
Basically. And so we added a 3D scanner, which is something called a structured light scanner. It's like a stereo pair of cameras and it projects a little pattern onto the sample and you can create 3D models that way. And so the sample stayed inside the glove box and we just scanned through the window and you're able to rotate the sample manually. The people reach through like the little glove ports, rotate the sample, scan, rotate, scan. And so with about 20 of the largest particles, we made 3D models without ever removing them from the glove box. And then they have mass balances, a way to weigh the samples inside the glove boxes. And we got density values that way. So that was our first hint. We saw a range of densities. We actually saw that the particles looked like the boulders on the surface. We saw these ones that looked really jagged, and we saw these ones that looked more angular and blocky and geometric. And right away we found, hey, these have different densities. That's what we predicted. All right, I think we're on the right track.
Awesome.
Part of this is just like confirming, did we get the stuff we saw on the surface? Like, is this representative of what we saw globally on the asteroid? And it was like, yeah, it looks like this is representative. And that's really exciting. And that's going to help us decide which samples we do want to put on our tab and take out and distribute to the science team. There was this whole down select process where we picked stones of interest, or SOIs as we call them, because everything has to be an acronym. So, we had these SOIs and we had density values on all of them and we started down selecting from there. We also tried to directly measure porosity in the clean room too. We built this device called a gas pycnometer. This was in partnership with the curator of meteorites from the Vatican Observatory, Brother Bob Mackey. Shout out to Bob. I'll send you a link to this so you listen later.
Hi, Bob.
So Bob is an expert in this measurement that it's much like the Archimedean principle where, if you have like a volume of water and you drop a solid in and you see how much the water is displaced, the volume of the thing you dropped in there, you can do the same thing with gas using the ideal gas law. And so we built a device that attached to the glove box chamber to do this measurement in a non-contaminating way. But unfortunately, our measurement plans were foiled by the unexpected nature of the sample because we used nitrogen as the gas to do this measurement, partly because we were required to do so. This was the only gas we were allowed to use. And the results we got were super wonky. The numbers didn't make any sense. And we eventually found that the samples, they were like breathing in the gas and it was like basically absorbing onto the surface. Like they had tons of internal surface area and the gas was basically like disappearing from the equation. Like it was depositing, at least this is our leading hypothesis. I think Bob's still working to understand, but the gas was basically like disappearing from the equation and the results didn't make any sense. So unfortunately, despite our best efforts, we did not get direct porosity measurements during this initial triage phase of the sample. That would have been super useful, but so we kind of had to, try other ways to do it.
Got it. Did you ever actually get to like put your hands in the glove box and like handle the material yourself?
I don't think. No, not at NASA Johnson Space Center. They have very strict rules there about who's allowed to put their hands in the glove box. But I was in the room pretty frequently and got to look at the samples.
Yeah.
Like couple feet away,
So
which is
cool.
pretty incredible. With the samples, though, that were distributed to the team, I eventually did handle the samples.
Got it.
Like some of them, I worked with right in my lab. And at that point, you don't have to keep them in a glove box anymore. And so some of them, you handle with tweezers and just kind of do your thing.
Nice.
Yeah.
I'm the kind of nerd that I'll rock hound when I'm out in the desert or out and about.
Yeah.
I'll find a cool rock and be like, neat. And I'll, take it with me, put it on my rock shelf. Yeah, I have a rock shelf. But I often think like, man, this rock has been sitting there for basically all of time
Yeah.
until I walked along and picked it up. And you got to, you know,
Now,
you got-
it's Jack's Rock.
basically, well, you got to handle some material that same thing, but on a solar system
Yeah.
scale. Like, it's kind of wild to me, and it's really, really cool.
I remember going in for the first time and seeing the samples up close, and it's like one of those moments where it's impossible not to just be grinning like an idiot the whole time. And the other people that were in there with me, some of the other scientists, it was their first time too, and we were all just glowing, like
Yeah, how could you
in
not?
our giant bunny suits, so you could only like see our eyes.
You see everyone smizing.
But I
you're
think,
like,
yeah,
"Hey!"
exactly. Yeah. That was really exciting. And it was shocking, like how dark the material was in person. Because the images you see of, taken by the spacecraft, they're always blown up and brightened to
Right.
make them look really nice. But up close, the stuff is black as charcoal.
Wow.
Yeah.
Okay. To figure out that it was, in fact, the insane level of internal cracks that was the discrepancy here, or the cause of discrepancy, you guys had to go to a team in Japan that did lock-in thermography? Is that...
Yeah, there were two measurements that were really critical to this paper. One of them was this heat flow measurement called lock-in thermography, where the goal there was to directly measure essentially the thermal inertia of the samples. And the same technique had been applied to the samples brought back from asteroid Ryugu in the Hayabusa 2 mission. And Ryugu and Bennu have a lot of similarities. So we were excited to do an apples-to-apples comparison. This technique, basically, you heat the surface of the sample with a laser, periodic, so the laser is pulsing.
You don't say.
Yeah. Yeah, it was foreshadowing for my career path.
For
I guess.
real?
And that basically creates like thermal ripples across the surface, if you image it with a thermal camera. And
You don't
the
say.
period of those thermal ripples and like the spacing and timing of them, you can calculate the thermal diffusivity and thermal inertia of the samples. So this technique was applied to a few different particles from the two categories that we thought, we were hypothesizing mapped to those two boulders on the surface of the asteroid, the really angular ones and the really rough, jagged ones. And we got thermal inertias that were way higher than what we had gotten on the surface of the asteroid. So we're like, well, okay, what's going on here? The asteroid was telling us that thermal inertia is low, and therefore they may be porous, but when we measure them, we get a high thermal inertia, kind of like other meteorites. So, and the Hayabusa 2 team had gotten the same result with the Ryugu samples. And so this took some pondering for a while. And I came to realize that this technique, it's probing the samples at a really small scale. Like it's only, those thermal ripples only emanate out a few hundred micrometers. Very small spot sizes, smaller than a millimeter. So, it's like measuring the properties at length scales of like a few hair widths, literally.
Yeah, hair's what, like 10 microns or something?
I forget. I'm not a hair scientist.
Wow,
Sorry,
dude, you told me you were a hair scientist. I thought I was gonna have an awesome head of hair after
Can't
this.
help you, man. The other really critical measurement was one that we call X-ray computed tomography. It's used in the medical field. It's been used for a while. It's like what they call a CAT scan or a CT scan, and it's literally a 3D X-ray of.
It's like the spinning
sample.
magnet, helium-cooled, crazy machine that will suck out your fillings.
No, it's not. It doesn't have to be helium cooled. These devices are, they can have one like the size of that little piece of furniture over there, and actually, if you've been to the airport where you haven't had to take your computer out of a bag,
yeah,
it's that exact scanner.
No kidding.
That's a 3D, that's a computed tomography scanner where it does a 3D X-ray, and they're able to basically sweep through the 3D, like do slices, and look at different depths through your bag and be like, all right, here's the laptop, and here's the stuff on top of it, here's the stuff below it. You verify that everything, none of it's a bomb or whatever it is that you like to fly with.
I love those machines.
Yeah, exact same technology, just measuring things at a much, much smaller scale. So NASA Johnson Space Center, this was Scott Eckley at Johnson Space Center. Shout out to Scott. These measurements were amazing. He measured dozens of the largest particles, and they also did it in a non-contaminating way, so it didn't count against anyone's tab.
Nice.
Where they basically packaged them up in these hermetically sealed vessels and wrapped them. It was like multiple layers of wrapping, and then they were able to put it in the instrument and scan right through the walls of these containers.
So like the samples had their own little like quasi spacesuits, Earth suits,
Kind of, yeah. They were these stainless steel vessels, and then they wrapped them in several layers of bagging, and yeah, it was a whole process to like. And they did a bunch of tests beforehand to verify that there would be no contamination introduced. So they did it with like some dummy specimens and made sure that they came out just as clean as they went in. And so that was a really enabling method, and that allowed us to look into the internal structure. And this is where we started to be able to map out the cracks, and we started to notice that the two different sample types, the angular and what we call the hummocky or the really rough ones, crack networks looked really different. And then I realized that those lock and thermography measurements are at a spatial scale that is small enough that, like, if you look at a rock and you zoom in and maybe there's a crack here and a crack here, the thermography measurement could be just right in between them. And it's basically not picking up the signature of all those cracks that are at a larger scale, going to be really influential in dictating heat flow and the thermal inertia of that material. And so I used the data from the X-ray scans, and I was able to basically extract those crack networks in 3D as like a computer product and simulate the heat flow through them with a computer model.
Wow.
And basically to understand like what are these cracks doing? What should they be doing to the heat flow? And if you then like basically combine that result with the direct lock and thermography result, you basically shove those two together, you can more or less reproduce what we saw on the asteroid. And so that's why I said earlier, like the idea that this is a combination of cracks and pores as the explanation was not like a crazy idea. The hard thing was proving it.
Yeah.
And that was really hard to like actually get data that proved, yes, it is a combination of, yes, these things are porous, maybe not as high as we thought. They're porous. They're like 20, 30% porosity, but they're also just really cracked. And that's the explanation. So they may not be as spongy or as fluffy as we thought. So if you crash into one with your spacecraft, it may compact a little bit, but it's not 50% porous. It's not going to just compact down.
Yeah.
So there are implications there for planetary defense. If we send a kinetic impactor, that porosity matters a lot. And that's one of the reasons, like, I hope that people who are listening to this, you're probably like, why do I care? You've said porosity 500,000 times on this podcast so far. That's one of the reasons we care about it, because if you crash into something, it's, there's a big difference between crashing into a sponge and crashing into a brick.
Yeah,
and so it's kind of like
informs how you are going to want to deflect something like that.
Yeah.
Like if it's going to absorb a significant amount of that inertia, momentum, I don't know, force from the impactor, then you're going to need a bigger impactor or some other method or
a different method. Yeah. So that's a big part of it. A big part of it was just making sure that we could map the samples back to what we saw on the surface of the asteroid and getting those thermal inertias to line up where we had the angular sample particles and the really rough particles. We found that those thermal inertias were consistent with what we estimated on the surface of the asteroid. So that was more evidence that, like, yeah, these are actually mapped one-to-one. Like we do have pieces of the two boulder types on the surface of the asteroid. So that was really helpful to just put things into context. And then, helping us moving forward to understand the big picture. Like, how do we interpret remote sensing data moving forward, telescopic data? If we see a low thermal inertia, now I think we're going to be a little more careful in making interpretations. You can't just do it blindly. You'll need to consider, like, what is the spectral type? And if it is a carbonaceous asteroid and you see a low thermal inertia, I think it is highly likely that it could be bouldery. It's just that these types of heavily cracked and porous boulders, they may be kind of an inevitability on these types of objects for various reasons.
That's fascinating. So how does all of this information change or inform how you think about AstroForge's target asteroids before we even attempt to get to one or land on one, or maybe even as we do? Or does it? Like,
yeah, I'm trying to think. I could just say not at all. No,
I mean, no, that's a fair answer.
I think that so physics are universal, even though the materials are going to be really different. Physics are universal, and what we've learned about asteroid Bennu has taught us about processes that are important on asteroid surfaces. The things that were responsible for creating those boulders and making them really cracked are things like thermal fatigue and processing and just the way that the material is held together. If we get to, for example, a metallic asteroid and we see that it is covered in a regolith layer, I think we know that if we touch down on the surface, that stuff is going to fly everywhere now
Right.
from the sample collection.
Right.
If we are able to bring a thermal instrument on our spacecraft, depending on the type of material that we see, I think we're going to do a much better job now in interpreting that data set. It's almost, yeah, it is. I'll say it is tragic that there is no like perfect Star Trek material analyzer device
Like
out
scan
there.
button.
Yeah, that just tells you everything you need to know. Every measurement technique is going to give you incomplete information. Camera only tells you a few things. Thermal instrument tells you some stuff. Spectrometer tells you a little bit. The combination of them tells you a lot more. And so just going through this whole process with asteroid Bennu, where we looked at it as a point source from Earth, and then we went there and we orbited it and looked at it from the spacecraft perspective. And then we actually took that material, brought it back, and we used the world's most cutting-edge, state-of-the-art facilities to analyze and understand all those observations we made up to that point. That's a critical part of the process, and it's something that we're going to have to keep doing. And each time we do it, we're going to get a little smarter and know how to interpret our data a little bit better. So I wish I could say that, yeah, this solves all our questions and we know exactly what we're going to find on a metallic asteroid. But no, there's no crystal ball, not yet. That's why we just got to keep going to these objects, because each time we do it, we're going to learn a crap load and get better at this.
I just keep thinking about what you said near the beginning of the episode, where it's like, man, we should be doing a bunch of these. Like, I really wish we can get there sooner rather than later. And that's part of the reason why I'm so excited to be here at AstroForge, is like, we are going to be sending a bunch of these probes to a bunch of these bodies and figure out a whole bunch of stuff out that we just don't know the answer to right now.
Yeah, I mean, that's one of the main reasons I'm here too. So I just want to see more asteroids.
Heck yeah. I think I know the answer to this based on our conversation thus far, but what would you tell your 2015 grad student self about where asteroid science and asteroid mining would be by 2026? And would you believe future you?
I think I would believe it, because in 2015, I remember we had a visit from someone that worked for Planetary Resources, which was one of the previous generation of asteroid mining and asteroid resource companies.
Right.
And I remember being really inspired by that, being like, that's freaking cool, and I want to do that. But I think I was kind of thinking about it almost, I wasn't ambitious enough. I remember at the time thinking, I want to be the thermal analysis expert for an asteroid mining company. But if I could go back, I think I would have said, that's great, but dream even bigger, because you don't have to stop just at like this one niche technique. Like, go for the whole thing. Don't just analyze temperature. Analyze everything about the asteroid. You're going to analyze samples from an asteroid someday. And after that, you're going to go and mine asteroids. So
awesome.
I think I would have been pretty stoked to hear that. Maybe a little intimidated, but that's fine.
I love it. All right. Well, is there anything I haven't hit or that you want to hit before we move on to mailbag? I mean, I like these more detailed discussions. Our audience hopefully does as well. At least my entire experience making content about spaceflight and putting it on the internet is that people appreciate it when you don't talk down to them. People appreciate it when you just straight up tell them what's up and like inform them, because people want to learn. So if there's anything I've missed or haven't thought of that you want to hit before we sort of put a bow on things with mailbag, by all means, be my guest.
No, I think I've maybe talked enough on this. So
No, you did.
I appreciate the opportunity though, and for those who have stuck with it, thank you for listening. And if you do have questions about the study, feel free to email me.
Yeah,
Andy@astroforge.com.
That's actually, you can totally do that. You can just do things. You can just do thermal analysis on asteroids.
And that's usually true for like any scientific publication. Usually the authors are thrilled to receive questions.
Love that. I really, like, science is so cool. I'm such a nerd. All right, let's jump into mailbag. And again, if you have questions, you can email Andy. You can also send your questions to mailbag@astroforge.com or comment on this video or tweet at us or what. You know how the internet works. If you have questions, ask them, please, because we like answering. Here's one from Thomas. The cracks in the boulders are what explained the thermal inertia mismatch. Does that mean the rocks are basically falling apart on their own? Like, could you theoretically just show up and the asteroid is pre-crushed and ready to go?
Yeah, they are breaking down over time on their own, so to speak. We think some of the cracks are very old, like from the parent body, the precursor to Bennu, because we see like mineral deposits. I'm not going to get into it, but we see evidence that some of them are old. But I think some of them are definitely newer or have been developing over time. There are two main processes that are probably making the cracks. One of them is micrometeorite impacts. So small impactors from, motes of dust, grains of sand, pebbles, up to, anything larger, are gradually just whittling away and stressing and, creating stress fractures and things like that in these boulders over time. But there's also a passive process that we call thermal fatigue, where the actual heating up and cooling down over and over for millions, billions of years, it thermally stresses these materials where each time it heats up, it expands and contracts, and that can create crack propagation over
It's like
time
the
as
same
well.
thing that cracks like a concrete sidewalk or what have you. If they don't put the grooves in there, like it's going to heat up and cool down and heat up and cool down and eventually crack.
That's one of the processes on Earth, though.
Also roots, tree roots.
Roots and
Don't make my analogy less good.
and in areas where it's cold, water and frost wedging are the real bad.
Oh yeah, frost wedging.
I grew up in the Northeast, and the roads could not survive.
Yeah, I believe it.
But yeah, thermal fatigue. This is something that was studied on the asteroid surface, where we saw lots of evidence of thermally induced fractures on the boulders, and it's being studied now in the return samples. My colleague Jamie Malaro is working on a paper on that. Actually, I think her paper is in a review right now, where she did a microscale model and compared that to the cracks that we see, and found that there's a lot of strong evidence that a lot of those cracks were created by thermal expansion and contraction.
So cool. Well,
so yeah, they're probably breaking down on their own over time. Yeah.
I'm just like, I wish I could hit the fast forward button to the point where Deep Space 2 is pulling up next to its target, whichever it ends up being, and we can sit there and nerd out super hard about all the things that we're learning. I'm very excited for that.
That's going to be amazing.
Cool. Well, this was amazing. Thank you, dude, so much for being on and taking time out of your busy day to talk to us about science.
Yeah, it's my pleasure. Thanks.
All right, that's it for this week. Thanks for watching. Again, if you have any questions for future episodes, tweet them, email them, you know what to do. And until then, we'll see you on the next one.